Hello everyone, welcome to Net 209, Scaling Your Network with IPv6. My name is Madhura Kale and I'm a product manager in Amazon EC2. Today we're going to talk about many things related to IPv6, but in the beginning let's go over our agenda so we all know what we're talking about. We will start with a quick check-in with the world since IPv6 was launched, where we are with v6 adoption around the world in different places. Then we're going to slide into more of a different topic where we talk about IPv6 and private networks, whether it's on AWS or even on premise. We're going to talk about depleting IPv4 space in your VPCs, in your private networks. And then we're going to combine those two to talk about how IPv6 can bring scale to this depleting resource. And finally, last but not the least, we're going to talk about some recent IPv6 launches at AWS so you're up to speed on what we have done so far. So let's get started. Where's the world with IPv6? You all must be familiar with this graph if you've ever monitored or tried to look at where IPv6 is. If you haven't looked recently, I'm happy to report that a third of the internet now talks IPv6. This is as of September. And compared to 3 years ago when we did a similar V6 session at reInvent, it was just about 20%. So you can see how fast things have changed in the last couple of years or so. Here's more numbers for you. The first one, 85.8%. That is the percentage of IPv6 deployment in US mobile carriers, so all the AT&T, Verizon's, Comcast, etc. of the world. 34.54 is the percentage, year-over-year growth percentage of IPv6 adoption. So compared to last year, the number you saw on the previous slide of 33%, that has grown, that has resulted from a growth of 35% since last year. 25, that's the number of countries that now support, that have devices that talk more than 30% of their devices talk IPv6, and 6 of those countries, actually my slide says 6, I checked this morning and it's already up to 7. There are 7 countries in the world that support IPv6 for greater than 50% of their users. In adoption, the top rankers, those 6 countries are India, United States, Germany, Belgium, Greece, Malaysia, and I may have Taiwan. The last number I'm going to throw at you, and I'll be done with numbers then, is 5.8 billion. That's the number of IoT connected endpoints that Gartner forecasted for the end of 2020. We're very close to that now, so we will see soon if that number is true or it's exceeded those expectations. Now that we've checked in with IPv6 and looked at what the world has been doing, let's talk about your networks and enterprise networks that you set up. We will dive into an entire private network setup and how we can use IPv6. This slide, IPv6 helps with IPv4 exhaustion on the internet and in your private network. It's a big title. Let's unpack that statement. Number 1, IPv6 helps solve for v4 exhaustion. I think that's a generally accepted fact now. We know this. This is why IPv6 was created. Simple enough. The second one is IPv6 in private networks. We typically don't think of IPv6 as public or private. We actually assume it's public. So we're gonna, in the next section, talk a little more about how that's how that may or may not be the best way to see it. And finally, IPv6 brings scale to depleting space in v4 networks. So once we talk about IPv6 and private networks, we're going to talk about depleting space and then get into bringing scale. So let's jump right in. IPv6 has globally unique address space, but globally unique does not necessarily mean public. I conducted a simple experiment where I created a dual stack VPC and a dual stack subnet. Then I created an Amazon EC2 instance that had a private IPv4 address and an IPv6 address as well. I did not create an internet gateway to this VPC. So here's what that looks like. If you look at the top left of this image, you see there's no public IPv4 address. In the middle, you'll see an IPv4 address that's private, the 10.0.0.59. And in the bottom left, you see an IPv6 address assigned to this instance that I created. Now, so first test, we're going to do a couple of tests. First test is I try to ping the instance from my IPv6 only laptop that's sitting here at home. I try to ping it, and as you can see, the request timed out. Sends forwards, it receives 0. A second test. I spin up a second instance in that same VPC, make sure my security groups are updated so that those two instances can talk to each other. Through the magic of private connectivity, I'm able to log into my instance and try to ping the first instance that I created. And what do I see? I see that those two instances, the ping is successful and those two instances are able to talk to each other. Let's do a quick recap. What we did was we added IPv6 to your virtual private cloud. We created two instances that can talk to each other over IPv6, but don't talk to the internet, kind of like a private network. The IPv6 address that you've assigned to these instances can be public, but it technically is not until you, 1, create an internet gateway, 2, create a route in the route table of your VPC to that internet gateway, and 3, change your security group settings to allow inbound IPv6 traffic, which is disabled by default. Once you do these 3 things, voila, there's your ping to the internet. That's successful. Our customers, when we talk to our customers about this, they still wanted this problem to be simplified further. So we launched something called the egress-only internet gateway. And if you're not familiar with that, it basically is something that helps you, instead of the internet gateway, if you use the egress-only internet gateway, it helps you create outbound connections to the internet over IPv6 while disallowing any inbound connections from the internet to your instances or to your VPC. The simplest way to see this is it's basically what a NAT gateway is in the v4 world, but for v6 without the address translation involved in it. Now, we've talked about adding v6 to your private network. You'll probably ask me why. Or you probably know why, but for those that don't, we have a lot of customers today that run into challenges with IPv4 space allocation, and I'm going to walk you through some of the challenges that they face and how they run into a scenario where they're basically running on scarce IPv4 resources in their VPCs. So here's what IPv4 private IP space looks like according to RFC 1918 space. There's a 10/8, that's 16 million IP addresses. There's a 172.16, that is 1 million IP addresses. There's a 192.168, which is 65,000 IPs. That's a lot of, you think that's a lot of IP addresses, but let's channel the network architect in our mind and see what that looks like for an actual enterprise network when you're trying to allocate the space for different parts of your organization. So say you start with the biggest space, that's 10/8. That is an equivalent of 65,000/24s. So when we are looking at large enterprise networks, we'll say, hey, now I'm going to start this cloud migration. Let me pick a chunk for AWS. And for that, I choose a 10/14, which is 1,000/24. This image is not to scale, but to give you an idea of just the allocation. Now, once you've allocated to AWS, you want to divide that into 2 pieces, one for production purposes and one for non-production. So what I'm going to do is create 2 chunks of /15s, which is 500/24s. Now, once I have these prod and non-prod environments, I would want to create special sections for each region, allocations for every region. So I have, assuming I have 2 regions, I'll create 2/17s, but I also want to keep in mind that, hey, we could expand to more regions, expand to different countries. I want to make sure as a network architect I have space to expand into. Similar in the non-prod environment. So I'm basically looking at every region with a 10/17 block, and that is equivalent to 128/24s. Now let's zoom in on a single region and see what that looks like for VPC and subnet and EC2 allocation from there. Here's your region, 10/17. You have 128/24s, which is also equivalent to 64/23s. And let's assign a /23 VPC, assuming you're okay with 64 VPCs per region. That's your 2 VPCs that are /23. Let's zoom into a VPC and allocate it to subnets. We're going to pick a /25 for the subnet, and we're basically creating 4 subnets. At a /25 size, your subnet has, including the reserved IP space, in an Amazon subnet, in an AWS subnet, you basically are left with less than 128 hosts per subnet. That's not a lot of hosts, that's not a lot of IPs, unique IPs to have in a subnet. You can argue that, hey, I could just allocate a larger chunk like I did initially to the AWS block. You can absolutely do that, but with 64 VPCs and less than 125 hosts, you're still left at a fairly small footprint that you can potentially run into challenges of space with. And we all know that it's not easy and efficient to allocate V4 space, so the problem is just exacerbated when you have these situations. There's also, our customers also run into problems where one company acquires another, or they have different parts of an organization that their IT infrastructure didn't talk to each other, but now they want to merge that setup, merge the entire infrastructure, but they run into problems like overlapping VPC IP address space, and then they don't know what to do. So here's where our superhero of the story comes to the rescue. That's IPv6, and we're going to talk about how we can use IPv6 to bring scale and to be able to grow this network beyond the size that we just talked about. Let's start with adding IPv6 to that VPC. There's, you must notice there that instead of the /23, I have now increased the size of my VPC to /15. And I've added an IPv6 CIDR to it, the 2001 DB8 EC2:1:/56. That rolls right off the tongue. And then with that, I create a subnet of the size 10/16. And obviously with an IPv6 CIDR that has a /64. And here we have our EC2 instance with a private IPv4 address and a public and a v6 address. Now our superhero is accompanied by the partner in crime, the transit gateway. What we now do is take 2 of these VPCs that have clearly identical v4 CIDRs in the 10/15s and the 10/16s, but unique IPv6 CIDRs with ending in EC2:1 versus EC2:2, and we create this transit gateway with 2 attachments. Attachment 1 to the first VPC on the left, attachment 2 to the VPC on the right. Our transit gateway route table, which I have manually created, points to the first VPC via attachment 1 and the second VPC via attachment 2. Now let's take a scenario where instance 1 in the VPC on the left is trying to talk to instance 2 in VPC on the right. You have your source IP as that instance and the destination IP as EC2.2:2::. one. Now what happens is the instance will then look up the VPC route table to say, hey, for the 2001 DB8 EC2:2 network, I need to go to my transit gateway attachment. Then, once at the transit gateway, it'll look up the transit gateway route table and say, oh, for EC2:2, I'm going to use attachment 2 to find my destination. And finally, in the second VPC, I'm going to reach my instance. Now, if we think about this and add more scale to this in terms of your typical enterprise hybrid setup. So let's extend this scenario to an enterprise hybrid setup and see that you have the same VPCs with 2 attachments. Now you add direct connect to it, and where you connect to your data center that's also IPv6 enabled, you connect to an on-premise office location or any other site via a VPN connection. And your transit gateway route table will basically have 4 attachments, each of them pointing to either a VPC in your AWS environment or your data centers and other on-prem locations via the other attachment 3 and 4. This is what your network setup can look like. You basically have a full-scaled enterprise hybrid network all running over IPv6 with IPv6 traffic talking end to end. Now, you must notice in that slide that on the top right, if you haven't noticed already, there's a little new flicker that's going on there. This is my segue into our IPv6 launches and things that we have built recently. So number 1 on the top right there is our VPN, site-to-site VPN product that recently announced support for IPv6 traffic for transit gateway attachments. The second launch recently is another super exciting one where the network load balancer now supports IPv6 connections from clients, and even last but not the least, we have Amazon ECS, a container service that now supports IPv6. Let's get into more details of these launches. Bring your own IPv6. This is something we launched a few months ago in the summer. Our customers, we used to support bring your own IP for our customers, but with IPv6 specifically, our customers thought it extremely important because with V4, private IPv4 space, the space is very predictable. You assign your own sort of 10/ prefixes, CIDRs to your VPC. With IPv6, Amazon provides a randomly generated prefix. So our customers, to get this predictability, wanted to bring their own IP addresses to merge like a full network from on-premise to AWS. So we launched Bring Your Own IPv6, where our customers can now bring your IPv6 address range that is registered with your regional internet registry to AWS. When you bring it to AWS, if you have a /48 size prefix that you bring, you can publicly advertise it. That means Amazon will also advertise it to the internet from our network. But you can bring a smaller prefix, and that won't be publicly advertised via the internet. You can always use Direct Connect and other private connectivity to then advertise that prefix back out to the internet. Here's what that looks like when you're provisioning your Bring Your Own IP CIDR. You select a publicly advertisable or no publicly advertisable choice. Site-to-site VPN with IPv6. Our site-to-site VPN connections to transit gateways now support IPv6 traffic. What you do is very simple. You create a VPN connection, attach it to that transit gateway. The connection itself will use IPv4 as well as IPv6, the tunnel setup, but the inside traffic within that tunnel will be IPv6. What you do when you're configuring this is you set, create the tunnel, you set tunnel options with inside IPv6, inside IP to IPv6. So as you can see in that, you pick your dynamic routing and your tunnel inside IP as IPv6. IPv6 support on network load balancer, very exciting. The application load balancer has supported IPv6 for a while now, and now we're bringing IPv6 support to the network load balancer. So remember where I talked about it right in the beginning of the slide, 33% of the internet now has IPv6 connectivity and talks IPv6. When you're running an application on AWS and you're thinking, hey, how do I reach these clients more seamlessly? The best way to do it is with a load balancer in the front that can present both IPv4 and IPv6 front end, so a dual stack front end, while keeping your VPC infrastructure still the same. It's the best way to quickly expand your base of IPv6 clients without making huge changes on your side on the network. So for V6 clients, you can now create a network load balancer that's dual stack. To configure it, super simple. When you're creating it, you name your load balancer, you pick your scheme, and you select your IP address type as dual stack. So you can either create a new load balancer. If you have an existing one, you can also add IPv6 to an internet-facing load balancer by just editing the IP address type and making it dual stack. You can either opt to use a random IPv6 address, just pick from your VPC CIDR. So when you're adding IPv6 to a network load balancer, you'd first have to go and add IPv6 to your VPC itself, and then when you change your load balancer, it'll either pick a random IP address for you, IPv6 address for you from the VPC CIDR, or you could choose to be very specific and say, hey, this is the addresses I want on my front end. So there you have it. IPv6 address, you can enter yourself from that CIDR. And finally, IPv6 on Amazon Elastic Container Service. So one of the things in the private v4 exhaustion that we talked about earlier with depleting space is containers that are responsible for a lot of IPv4 consumption or IP address consumption. And with more and more adoption of container services and our customers building scalable applications using containers, we see this as a problem that needs to be solved. And we started with Amazon ECS, where ECS now supports IPv6 in Amazon EC2 and Fargate in the AWS VPC mode. So traditionally, the host mode of ECS always supported IPv6, but now we bring it to the more popular AWS VPC mode. With that, what you have to do to enable IPv6 on your cluster is basically just add your IPv6 addresses to your VPCs and subnets. If you have your settings, you can, when you're creating, you can obviously select your VPC and subnet when you create your cluster and tasks. When your auto-assigned settings for your subnet are actually enabled for IPv6, Amazon ECS will automatically add IPv6 addresses by default. Like, you don't have to change anything. We're trying to simplify the whole process when you select a subnet setting. Amazon ECS picks up that same setting to enable v6 on your containers. And just for kicks, here's our first test that we ran with the first ever ECS task that's running on Fargate with IPv6. As you can see, there's an HTTP over IPv4 that works, and so does the one with IPv6. So we're super excited about this. We're going to do a quick recap of all the services that support IPv6 today. We have EC2, S3, VPC are very fundamental services that support IPv6. So does Amazon CloudFront on the edge. In load balancing, the application load balancer always did support IPv6, and now we're adding the network load balancer as well. We talked about Amazon ECS. On the edge, we have more services like Shield, Route 53, now Site-to-Site VPN, and Web Application Firewall that support IPv6. Other services, not limited to any type, is IAM supports IPv6, Transit Gateway obviously does, workspaces and Direct Connect and AWS IoT. So with that, I would like to conclude my session. Thank you very much for watching. I hope you learned something new today and had something to take away from this session. Please don't forget to fill out the survey at the end. We'd love to get feedback and then build on it. Thanks a lot.